Let us try to understand deadlock prevention in transaction processing. So, how was the deadlock happen? Or what is the okay? How do you find there's a deadlock? So, there's a wait for graph or graph-oriented representation can help us to understand whether there's a deadlock. In the example indicated over here, there are two processes. Process P1 is actually waiting for the resource which is held by process P2, and process P2 is actually waiting for the resource 1 which is held by process 1. So you can just observe in the diagram. Okay, so process 1 is actually waiting for this, but this is actually utilized by process P2, and process P2 is waiting for resource 1 which is actually held by process 1. So you can just observe this as a cycle. So once there's a cycle, it means that there is a deadlock. So whenever there's a cycle of resources and process, then there is a deadlock. So as I indicated, it might be only two transaction or multiple transaction also. Uh, in simple, deadlocks can occur when two or more transaction wait indefinitely. So they're waiting indefinitely for resources held by each other. As indicated earlier, two-phase locking protocol, yes, it ensures concurrency control, but the disadvantage is deadlock. So how do I overcome it? Then there are different mechanisms. One of the important timestamp. If you're using a timestamp based schemes, then there are two mechanisms. One is called as wait die, and the other one is wound wait. Wait die. The second one is wound wait. So what is the meaning of wait die scheme? Okay, what we do? So in this case, in wait die scheme, the older transaction, so the timestamp which has a lower value, request for a resource held by a younger transaction, it is allowed to wait. So indirectly, you are allowing the older transaction. So the transaction which started early, okay, so will wait. But if it's an younger transaction request for resources, which is held by a older transaction. So you have started after some transaction T1 has started, then it is aborted. So and it is restarted with the same timestamp. So you allow it to restart. So the concept is very simple. The older transaction is allowed for the resources. The younger transactions are aborted. So frequently you abort it. So that's the disadvantage. But the advantage is, okay, you will never get a deadlock. Like for example, there is transaction T1. Okay, so the timestamp is 10 milliseconds. So it has started in 10 o'clock. Let us assume that it has started 10 o'clock. So it has acquired resources R1. So our resource R1 is acquired by T1. Now T2 will start. Okay, T2 will start. Okay, it will allocate what? Okay, resource R2. It requires R2. So and hence it is actually okay. It you're allowing R2. Okay, because R2 is a different resource. So transaction T2 is allocated this. So you can observe transaction T1 has been allocated resource 1. Transaction T2 has been allocated resource R2. Now let us assume that T1 wants resource R2. T1 wants resource R2. Okay. Now it will find out what is the timestamp of T2. Let us assume that it started in 20. Okay, 20 hours. But which one is the older one? Older one is T1. So since older is T1, it is allowed to wait. It is allowed to wait. Okay, let us assume that T2 actually requests for R1. Okay, T2 will ask for R1. So if T2 asks for R1, it will check for the timestamp. Who is okay? R1 is actually utilized by T1. Okay, it has been actually acquired and held by T1. But T1 is a older transaction because the timestamp is 10 milliseconds. So 10 o'clock, T2 is 20. So T1 was the one which was started early. So since T1 is okay, started early, T2 will be aborted. It dies. So making sure that transaction T1 will get R2 also. So that's the advantage of using, okay, that's the advantage of using wait and die scheme. Okay, wait and die scheme. Okay, wait and die scheme. So the older transaction will wait. Younger transaction, if at all, if it asks for resources, it will be terminated. Okay, the older waits, younger dies. That's the rule. So this is one more example to illustrate. P1, okay, it started in TS of 10. Okay, P2 which started older. Fine. Okay, so it will not wait. Okay, so TS of T1. I'm just giving you one more example. TS a timestamp T1. Okay, has started early. T2 started next. If T2 request for a resource held by T1. Okay, T2 is aborted. So that's the example that I showed you. T1 requests for resources which is held by T2, then T1 is allowed to wait. So I know that if you are not allowing that cycle, okay, so the cycle that I showed you with respect to deadlock, that will not be allowed in this particular instance. So this is one more graphical representation to indicate wound wait deadlock. So wait and die, what is wait and die? I feel I've given you the wrong example. Wait and die, what does it do is, okay, wait. Who waits? Older transaction will wait. Who dies? The recent transaction will die. Recent transaction will die. So wound wait scheme, okay, is the other way around. When older transaction requests for resources held by a younger transaction, it wounds itself. So it's something like the younger ones is allowed to continue, and the older transaction is actually dies. That's the reason why we call it as wound weight. Okay, so the first one is wait and die. Okay, you should always think about a older one. So in this case, older is wounded. So indirectly, it means that it gets aborted. For an younger and a transaction request a resource held by an older transaction, it is allowed to wait. So the reverse way around. So usually this is dangerous. Wound weight is actually dangerous because it eats up a lot of time. Yeah, okay, it's something like you're botting the transaction which started early. So you are actually deleting it. So in simple representation, you can just observe. So T1, T2 is there. T1 request for resources held by T2. T2 is rolled back. Kindly understand. Okay. T2 request for resource held by T1, T2 is waits. Okay, indirectly, you can, like, if I'm trying to indicate it as a very simple representation, this transaction T1, this transaction T2. Okay, good. So T1, okay, is holding resource R1. There's absolutely no conflict at all. So you're allowing R1 to be held by T1. So let us assume that T2 will actually request for R2, resource R2. This will also be given. And let us assume that this was started at 10 o'clock. This was started at 20 hours. So which one is older? T1 is older. So T1 request for a resource held by T2. So I actually request R2, correct? So you can just observe T2 is rolled back, okay, wounded, okay. Uh, so T1 request a resource held by T2. T1 request a resource held by T2. T2 is rolled back, wounded. If T2 requests a resource held by T1, T2 waits. So if indirectly I request this, okay, R1. So this will actually T2 will wait. So, okay, T1, okay, this is wrong actually. T1 is rolled back, okay, because, okay, the older transaction is allowed. Okay, T1, okay, I'll just try to repeat it once again. Let me clear it. There's a small change. Okay, T1 is rolled back. Okay, it is not T2. So T1 is actually holding resources R1. T2 is actually holding resource R2. Now T1 will request for R2. R2 is actually held by transaction T2, but T1 was started at 10 o'clock. T2 has started 20. So which one is older? T1 is older. Okay, so you request fine. It will know that, okay, it has been held by an younger transaction. So T1 gets aborted. T1 gets aborted. Okay, so that's the advantage of using this particular methodology. So wound weight actually, okay, is a problematic instance because the older transactions, because when I say older transaction, it would have executed a lot of steps. So you're making that to, okay, a rollback. Okay, so you get wounded, so which is not acceptable. Uh, and hence, the first method is generally used. So we don't generally go for wound weight scheme. We go for, okay, weight die scheme. Okay, weight die scheme is been used. Of course, it depends upon the applications. Generally, weight die scheme has been preferred. So this is how it looks like.